Okay, so from last time, so we talked about the column space for any matrix A. We talked about this column space and the null space. We also talked about the dimensions of these two subspaces, and so more precisely, so we also studied how to find the basis of each of these subspaces. Okay, so from last time, if if I have an m by n matrix, rank R, then dimension of the column space is R, and dimension of the null space was n minus R. So that was it. And today, we will be turning to section 2.4, which is about the four fundamental spaces. So what are these four fundamental spaces? So, so previously, once a matrix is given, so we were able to associate two different subspaces, namely the column space and the null space. And actually, we can associate two more subspaces from this matrix A. So, therefore, combining all these four spaces, so we could name it the four fundamental subspaces of matrix A. So, what are these four fundamental spaces? I'm going to give you the definition first. Okay, so this is my definition. I have a matrix A, so which is n by n, and whose rank is R. The column space. So what is columns? We know column space. So column space is a subspace of R M. Yeah, these numbers are very important. So I have M rows. Therefore, yeah, this is subspace of Rm, which is spanned by the columns of matrix A. Okay, this which is good. And the null space is, well, again, it's collection of all vectors from Rn such that multiply by V equals to 0. So this is the null space. Yeah, clearly this was again a subspace, and a subspace of Rn. All right, and today I want to introduce the two more subspaces, which is the row space and the left null space. So what is the row space? Row space turns out to be a column space of A transpose. Okay, very easy. So, well, what are the columns of A transpose? The columns of A transpose is nothing but the rows of A. So now I understand why they call it the row space. So, and the row space is denoted by column space of C A transpose. And clearly this is the subspace of Rn. Well, I really want to write it down by R of A, but well, I really want to, at the same time, I want to respect the notation of the Professor Strang. So I rather call it by C of AT. Okay, so this is the row space. And the one last thing is the left null space. So left null space of A is the null space of AT. So A transpose. So well, since this is a null space of A transpose, so it is very natural to denote by N of A transpose. Clearly, this is the subspace of Rn. Okay. Okay. So in order to be a member of the null space, so Y is a member of, so Y is a member of the null space, which is this, okay? But taking the transpose of everything, So you can understand the left null space like this, which is, this is a left null space is a collection of all row vectors such that multiplied by A to the left, which equals to 0. Collection of all such vectors is called a left null space of A. Okay. So this is the left null space. All right. So let me try to understand these four spaces let me try to write down each of these four vector subspaces of this matrix. So every every matrix has these four subspaces. Let me try to find these four fundamental. So these four spaces, we say they are four fundamental spaces of matrix A. And let me try to find the four fundamental spaces of this matrix. I mean, to find the subspace, I mean by try to find the basis of the space. Okay. What are the basis of what are the basis of null space of A? Well, to find the basis of null space, well, we must be able to solve the space of the set of all solutions of A times x equal to 0. Solution of that linear system must be the null space. But in this case, my matrix A is very easy. Hold on. What is the rank of this guy? The rank, since I have only one linearly independent columns, rank means the number of pivots. At the same time, that means the number of linearly independent columns of the matrix A. And clearly, I can see only one linearly independent column. So therefore, the rank of this guy must be 1. And also, the column index of the number of columns of this matrix is 3. Therefore, null space of this one has to be 3 minus 1, which is 2-dimensional subspace. Okay, so which means I must be able to find 2 basis vectors for this guy. Okay. In this case, well, since the matrix is very easy, so I can find these 2 basis vectors by direct computation. Okay, yeah, I guess these two vectors are the basis of the null space. If you do not understand, just try to multiply these columns to the right side of this matrix. Then the answer has to be 0, right? And clearly, these two guys are linearly independent. So it is safe to say these two things are the basis vectors of the null space. Okay. Okay. All right. Okay. Okay. What about the column space? So column space is very easy because, well, by definition, column space is a space spanned by columns of matrix A. But here I can only find one single non-zero vector. So this is my basis of the column space. Clearly, the dimension of the column space must be which is the one dimension. The dimension of the column space must be the same as the rank of the matrix. So clearly, it suffices to find just one single vector for the basis. Okay. What about the row space? I have two rows, but there is only one non-zero row, which is 1, 0, 0. Therefore, the answer is 1, 0, 0. Yeah, because of its naming. So we always call it the row space. So I always tempted to write that. So I always tend to write down the basis vector as a row vector, not a column vector. But well, to be precise, this is the column space of A transpose. So, well, I feel like I have to write down everything in column vector. So please let me write down my answer in columns. Okay. Lastly, the left null space, which is a. So I will need. So what is the dimension of this guy? This guy. So this is 2 by 3 matrix, right? So therefore, this is 3 by 2 matrix. Hold on. So what is the rank of A transpose? I don't know. So well, I do not know yet. But in this case, since my matrix is so easy, so I will need to find a row vector that multiplied by A to the left equals to 0. In this case, there has to be only one such vector. 0 and 1. Sorry. So even though I told you the row vector, but yeah. So if you take a transpose of this guy and multiply by A to the left, then the answer must be 0, right? Right? Okay. Can you find any other vector? No, I guess that's it. So this is only one linearly independent vector that spans the left null space. All right. In this example, so I was able to find the basis of these 4 subspaces mainly because my matrix A was so easy. But what if my matrix A is like getting more and more complicated? Well, even in that case, you must be able to find the basis of these 4 vector spaces, these 4 subspaces. Why? Well, because we now know how to find the basis vectors of this guy and that guy. And finding the basis of these 2 subspaces is merely taking the transpose of the original matrix and apply the same algorithm. Then you can find the basis of these 4 spaces. But there can be, well, some clever idea regarding the basis on the dimensions. Well, also regarding the basis on dimension of these 2 spaces. Well, especially in order to discuss the dimensions of these 2 spaces, then I must be able to find the rank of not A, but rank of A transpose. How the rank of A and rank of A transpose related? This is very important question. So today I will try to begin my lecture by starting the answer the question. The relation between the rank of A and rank of A transpose. The first things first, the row space of A. Let me try to talk about the row space and the left null space. The first row space. To discuss the dimensions of the row space, I guess I will try to explain this theorem first. I have an echelon matrix. U is the echelon matrix of A. Then the row space of A is the same as the row space of echelon matrix U. This is my first claim. Why is that? First, you will need to be convinced that the every law of U, the laws of U, they can be written as a linear combination of laws of A. Why is it? Aha, this is easy. So, well, U is obtained by applying the elementary law operations towards the laws of original matrix A, right? So, I mean, in order to obtain any law from the echelon matrix U, then you will somehow need to add or multiply. So multiply by some scalars to the numbers, to laws, and add it to some other laws. This is how you obtain atypical laws from the echelon matrix U. In other words, by doing so, U is obtained, well, it is actually a linear combination of A, okay? This is mathematically equivalent to say that a sequence of elementary matrices from E1 to EK such that U is EK E1 of A. So, well, so this statement and that statement, so they are equivalent statements. Okay, so therefore the low space of U, this is low space of U. So, and every law of U is a linear combination of the laws of A. Therefore, this guy must be subspace of the low space of A, right? Okay, good. And for the other side of inclusion, I will begin from this equation. Well, and as you know well, so this is n by n. So each of these elementary matrices, they must be n by n square matrix, and they are all lower triangular matrix, and their diagonals are all ones. Therefore, the inverse of each of these elementary matrices must be another elementary matrix, right? So A can be written as E1 inverse, E2 inverse, EK inverse of everything times U. So, what do you know from this equation? So what do you know from this equality? So that means if this equality means that every law of U is a linear combination of laws of A, then this opposite equation implies that every law of A can be written as a linear combination of laws of U. Okay. So C of AT is C of UT. Therefore, those two spaces must be the same. Okay. Very simple, but very useful fact. I have two immediate corollaries from the theorem. The dimension of the low space is the same as the rank of A, which is the same as dimension of column space. Those two spaces, they have the same dimensions. Okay, so why? We know that the dimension of column space is the same as the number of pivot of echelon matrix of U and echelon matrix of A. So this is the same as the number of pivots. Now, how many pivots do we have? So you know that U is a staircase-shaped matrix, and so number of pivots is the same as, and it is very clear to me that number of pivots is the same as number of linearly independent rows in echelon matrix U, right? So if I have R pivots in U, then there must be R independent rows in matrix U. However, the number of linearly independent rows of U is the same as the number of pivots. D1, dr. So I have precisely R many independent rows from matrix U. So I have precisely this many independent rows of U. That means dimension of row space, which is the same as dimension of the dimension of the row space of U is the same as dimension of the row space of A. This is the same as rank of A, which is the dimension of column space. Those three numbers, they are all the same. Okay. All right. Now, this very easy result gives us very surprising intuition. No, not intuition. This is very easy corollary leads us another very surprising result. That is, what is that? The dimension of the row space of A, so by is the definition, can be considered as the number of linearly independent rows of matrix A, right? Dimension of row space is the number of independent rows of A, right? But this number turns out to be the same as dimension of the column space. That means and this number actually means the number of linearly independent columns of matrix A. So for any matrix A, the number of linearly independent rows must be the same as the number of linearly independent columns. Isn't that surprising? No? Yeah, for me, this was very surprising fact. But just try to write down any random matrix you can possibly think of. Then the number of independent rows is always equals to the number of independent columns. Well, if you have your textbook, and if you read your textbook, then Professor Chang, he always emphasized that this is so, that was so amazing fact, surprising fact, even to him. Yeah, so maybe it deserves some time to put an emphasis on this. The number of independent rows is always the same as the number of independent columns. Because rank of AT, this number means this number. This is dimension of the row space, but this is dimension of the column space. So rank of A and rank of A transpose, they are all the same number. So okay, all right. So this also gives us some sort of intuition towards the ranks, the number, the rank. So suppose that you have the n by n matrix. And well, the n by, so two numbers, the two numbers define the dimension of the matrix, m and n. And if you believe in the statement, then the rank of any matrix cannot exceed the smaller number between these two. Okay. All right. Okay. Okay. So this is about the row space. Now, I will turn to the left null space. The left null space of A. NAT. Well, as always, this is an m by n matrix. First, what is the dimension of the left null space? The left null space, by its definition, the definition of the dimension of the null space is the number of columns minus rank of the matrix. Okay, and since this is an n by n matrix, as therefore A transpose must be n by n matrix. So this is m by m minus rank of A transpose. This is m minus rank of A. Now we know the dimension of the rank of now we know the dimension of the left null space. Then how do we find that? How do we find the basis of left null space? The most straightforward algorithm to find the null space basis of left null space is try to solve the system of linear equations like this. If you solve this system of equations, then you know how to do, and find the you can find the free variables, and each of these free variables can be associated to the basis vectors of the space of AT. So this is how you find the basis vectors of this guy. Yeah, this is one way, very straightforward, right? But I introduced some different algorithm to find the basis of left null space. What is this? First, we begin from the echelon matrix of U. Echelon matrix U of matrix A. Consider the echelon matrix U of A. If you think of a echelon matrix, then this is the same as the LU factorization. Well, not precise LU factorization, because LU factorization is only for, technically LU factorization is only for the square matrix. But this is a rectangular matrix, but you know the idea. So you can still apply the same idea to find the echelon matrix of U of A. So to do that, you have a sequence of elementary matrices. Such that EK minus 1 E1 times A is U. So now you have this many elementary matrices. And what are these? Each of these elementary matrices, they are square and lower triangular matrix. Therefore, multiple of all these matrices. So multiple of all these matrices is still going to be the lower triangular matrix. So this is a lower triangular. And the most natural way to name this matrix, it must be the L inverse. I'm gonna give the name of this guy by L inverse. Okay. Now let me magnify the left-hand side of this equation. This is the L inverse consists of this L, it must be M by M matrix. So I want to consider this matrix as a collection of M row vectors times A is and this is my U. So this is L inverse, and this is U. I have, well, rank of, I must say that rank of my matrix A is R. So I have precisely R non-zero rows on the right. So magnifying this equation, I have this one. Does it any help to find the basis of the left null space? Oh, yes. Because, well, this guy multiplied by this, well, this single row multiplied by this is going to be the first row on the right, right? The second row multiplied by A is going to be the second row on the right. And it goes on like this. That means if you multiply this n plus 1, n plus first row to A, then it's going to be the zero vector. So Li times A is going to be the 0 for I R plus 1 to n. Right? Okay. So I have, so how many such equations do I have? So I have precisely m minus r such equations. And each of these rows from r plus 1 to m, or these guys are linearly independent. Why? Because this L inverse was chosen to be the lower triangular matrix. So these row vectors, they are all linearly independent. And these vectors multiply to A to the left, then is equals to 0. So, and number of such vectors is precisely n minus r. So it is okay to say that these vectors from L, r plus 1 to Lm, they form a set of bases of the left null space of A. Why? Because the dimension of this guy was precisely n minus rank. Okay, so so L, these rows is a set of bases for the left null space and 8. Okay. By doing so, I was able to find the basis of the left null space. Okay. I have prepared a little example of this. This is my matrix, 3 by 4 matrix. We have seen this matrix many times before. And by taking the echelon matrix of U, this is the echelon matrix. And I can also think of the LU factorization, so-called LU factorization of this matrix. This number is 2 because I multiply this guy by -2 to the first and add it to the second. So this, because of those reasons, so we were able to pinpoint these sub-diagonal entries of this lower triangular matrix. So you know how to find these numbers. And if you invert this number, then I have this equation, right? Now, from this last equation, can you find the basis vector of the left null space of A? Yes, because since the last row on your right is the 0 row, that implies this guy multiplied by A is going to be 0, right? And is there any more basis? No, this is it. Because this is rank 2 matrix. Therefore, and n minus 2, which is 1. So we know that left null space of A is 1-dimensional. So this is the one and only basis vectors of the left null space. So left null space is spanned by 5 minus 2 and 1. Okay, good. Okay. So we now know how to find the base of, we now know the base dimensions of those 4 fundamental subspaces. And we also know how to find the basis of those 4 fundamental spaces. So I will summarize all the result like this. So summarizing, so if A is an n by n matrix with rank R, then these are the dimensions of those 4 spaces. Also you have to be very careful choosing these numbers. So the NA is Rn, it's the subspace of Rn. So this is n minus R dimensional, and this is subspace of Rm, and then those two guys have the same dimensions, and this is subspace of not Rn but Rm, therefore, which is n minus R dimensions. And even though I have omitted it, but also you should be able to find the basis of those 4 fundamental spaces. So these are so important. So we say these are the 4 fundamental spaces. All right. So even though we talked about a lot about the dimensions of the basis of these four fundamental spaces, but there's one more thing to add about the geometric picture of those four spaces. First, we want to focus on the relation between the column space and the left null space. These two spaces are very much related to each other. Actually, so if you can find one of these two spaces, then you can find the other. Oh, by the way, those two spaces, the column space and left null space, they are the subspaces of the same Euclidean space, right? So how those two guys are related? So this is very interesting question. And there is a big slogan from our textbook, and it says the column space is orthogonal complement to the left null space. Actually, I copied this. I copied this slogan from our textbook. So this is somehow sounds very mysterious. So what do I mean by complement? Well, in set theory, so if suppose that you have a big set and suppose you have a small subset contained inside. In that case, if I say complement, then you know what I mean, right? All the other guys outside of that small subset. But what do I mean by complement of not a set, but complement of a subspace? So first, I will try to explain what I mean by complement of a subspace. And also, what do I mean by orthogonal subspaces? Okay. So if you have ever attended to the any multivariable calculus course, then you know what I mean by two vectors are orthogonal to each other, right? Well, they form a 90-degree angles. But what do I mean by two? I'm claiming that not two vectors, but two spaces are orthogonal. What do I mean by that? So I have two interesting concepts going on, lurking underneath in this slogan. So I will try to explain them one by one. First, I will try to explain the notion of the orthogonality. First, in order to introduce the notion of the orthogonality, I will need to introduce the inner product. Do you know inner product? Well, many of you know that already. So for any two vectors, x and y, from the Euclidean space Rn, the inner product of x and y is defined by x transpose y. So you have to remember those two vectors are all column vectors. Therefore, x transpose y is actually the row times column, and which turns out to be a component-wise multiplication and taking summation. So this number is the inner product of x and y, right? Well, so, and obviously x transpose y is the same as y transpose x. So they are the same thing. So inner product is like commutative. Okay, so, and we say two vectors, x and y, they are orthogonal to each other if and only if their inner product equals to 0. Okay, so this is our definition. Now, let me go back to the column space and the left null space. I have a m by n matrix A, and I want to consider my matrix as a collection of columns from A1 all the way up to AN. This is my matrix A. Okay, then I have chosen any random vector from the left null space. So in other words, A transpose times A equals to 0. Okay. And again, this is same as Y transpose times. Well, I told you this was my A. So, oops. This is what? The result can be understood as, so what is the result? This is the row vector times n minus n matrix. So this is 1 by n matrix. So, and each of these components is Y transpose A1, Y transpose A2, Y transpose AN. Inner product of each of these vectors turns out to be the component of the resulting row vector. And we require this guy to be 0, right? Because Y was a member of the left null space. Okay. In other words, Y transpose AI equals to 0 for I from 1 to n. This is very interesting result. So at least to me. Why? Why is it so interesting? Because if you have chosen any random guy from the left null space, then, and also you have to remember that each of these columns, they are the spanning vectors of the column space, right? Linear combinations of these guys spans the entire column space CA. And Y inner product of each of these spanning vectors equals to 0. So therefore, the only possible explanation is the vector Y is orthogonal to not a single vector AI, but the entire subspace CA. A vector Y is orthogonal to entire subspace, right? But here I have not put any restriction on Y. So every random element Y is orthogonal to every spanning vectors of column space. Therefore, in this sense, I can say, I really tend to say that entire subspace and entire subspace left null space is orthogonal to the entire subspace of column space of A. So those two space, I'm not talking about just two vectors, but I am talking about two subspaces are orthogonal to each other, right? So Y is orthogonal to all vectors in CA. And this is the definition. I have two subspaces, U and V, and those two subspaces are they live in one ambient vector space V. U and V are the subspaces of vector space V. And if every guy in U is orthogonal to every guy in W, then we say those two spaces are orthogonal to each other. So if you believe in this sense, we say column space of A is orthogonal to the null space of A, right? So this is what I mean by two spaces are orthogonal. So the proposition, which is CA and NAT are orthogonal subspaces of Rm. Okay. All right. Also, this is very easy observation, which is if two subspaces U and W of vector space V are orthogonal, then U intersection with W, you can find only one single vector in this space, the zero vector. Also, I will try to justify the statement. Just choose any random element from the U intersection W. And I want to claim that this guy, inner product with itself, must be zero. Why? Because by definition of the orthogonality of two subspaces, so every guy in U must be orthogonal to the every guy in W. But V can be considered as a member of U and member of W at the same time. So therefore, V inner product with itself has to be zero, right? And by the way, what is this? So any vector inner product taking the inner product with itself, it can be considered as a magnitude, length of the vector, right? And there is only one vector whose length equals to zero. That is the zero vector. Okay. So V must be the zero vector. All right. Okay. Very easy. All right. So we somehow understand a part of the slogan. So column space is orthogonal to the left null space. By the way, what do I mean by they are complement to each other? So now this is time to explain the complementary subspaces. So in order to do that, I want to talk about the dimensions of these two spaces. Hold on. Oops, sorry. Let us suppose that the rank of matrix A is R. Then we can find the basis vectors of the column space and the left null spaces. V1 VR a basis, set of basis of column space, and since this is R dimensional, so this rank is R, so this is R dimensional, and the left null space must have the M minus R dimension. All right. Now, what I want to claim here is, well, let me just consider the union of these two sets. And I want to claim the union of these two guys, now which consists of the precisely m vectors. I claim that these m vectors are linearly independent. To do that, let me consider this linear combination. CR VR plus D1 W1 plus D M minus R W M minus R equal to zero vector. Let me consider this vector equation. If I can show that all these coefficients equals to zero, then that means these vectors are linearly independent. How? Yeah. Then this is okay, so sending all these guys to the right, so I end up with this equation. So these two guys are the same means, so this vector equals to that vector. Oh, hold on, but this is a member of, this guy is a member of a column space, and the right-hand side, this is a member of the left null space. And this guy equals to that means this vector and that vector, which is exactly actually the same vector, must lie in the intersection of this guy and this guy. So, and what is that vector? The only vector that lies in the intersection of these two must be zero vector. So this guy must be zero. And since we have chosen this guy as a basis of CA, so they are automatically linearly independent. Therefore, this guy equals to zero means that C1 to CR equals to zero. And this guy equals to zero means D1 to Dm minus R must be also all zero, right? C1, CR, and D1, Dm minus R is zero. So this is the union of these two guys, these two sets. And what we know now is that I have m vectors, and all these vectors, they are actually the member of Rm, and they are linearly independent. So these are the basis of Rm. Okay. So this implies for any vector in Rm, we can be written as a sum of column vector, sum of member a vector from column space and plus vector from the left null space. So every vector can be written like this. And this decomposition must be unique. Why? Because these are the basis vectors. Right? So this is what I mean by the null space and so this is what I mean by the column space and the left null spaces are complement to each other. They have, well, most of them, they are subspace in Rm, but their dimensions are complementary, right? The first one is this guy has the m dimension, the other one has m minus R dimensions. And so, and every vector in Rm can be written as uniquely decomposed as written as a sum of the column vector and the left null space vector. So in this sense, I say those two spaces are complementary to each other. So, column space and null space, they are orthogonal complement that lives in the ambient subspace, ambient space Rm. So this is, yes?
I think I just missed it, but why is the two vectors, it lies on the HDA and then A transpose, and why their intersection should be zero?
Why intersection of these two are zero? Because they are orthogonal subspaces. Yeah, okay. Okay, good. So it goes like this. Just one more thing. Sorry, this is a little digression. This definition doesn't appear in our textbook. But I believe this is the right time to introduce the notion of direct sum. Suppose that I have two subspaces of vector space V satisfying the following two conditions. U intersection W equals to 0. Equals to 0 vector. And every vector in vector space V can be uniquely written as the sum of vector in U and vector in W. So if these two conditions are met, then we say vector space V is a direct sum of U and W, and which is also written as V is U direct sum with W. So this is our notation. This is direct sum. Okay, so I'm gonna give you small pictures of the direct sum. I have so this is my ambient space, which is R2. Suppose that there is one subspace. Well, maybe this guy is spanned by, well, standard unit vector, E1. And I have another subspace. W. So this is another subspace. Maybe this guy was spanned by, well, this vector. I don't know, maybe. Anyhow, I have these two subspaces in R2. And is it okay to say that R2 is a direct sum of U and W? What do you think? Yes. Yes. Because, well, U and W, they only intersected the origin. And maybe any random vector in R2 can be written as a direct sum, well, can be written as a sum of this guy plus this guy, right? Every vector in R2 can be written as a sum of vectors in the U plus vector in W, right? So U and W, they are the direct sum of, so R2 is a direct sum of U and W, okay? But are they or U and W also gonna complement? No. Even though they are direct sum of U and W or R2 is R2, but they are not orthogonal complement. In order to be orthogonal complement, then U and W must be direct sum of U and W must be R2 itself, and on top of that, U and W must be orthogonal to each other. But clearly they are not orthogonal, right? So they are complement to each other, but they are not orthogonal, right? So, well, if you understand this slogan actually tells us very much information about the column space and the left null space. So let me consider this. Oops. Oops. Suppose that this is my column space. So if this is my column space, then can you imagine the shape of the I don't know. So I am not pretty sure that if so shape is the very right mathematical word or not, but well, can you imagine the shape of the left null space of matrix A? Yes, because there is only one subspace in R3, which is orthogonally complement to this guy, right? So being orthogonally complement is much hard, much strict condition than just the direct sum. Okay. So therefore, because the column space and null spaces, they are orthogonally complement to each other. So if you can pinpoint one of these two spaces, then that means you can automatically find out the other one. Okay. All right. So, oh, by the way, the row space is orthogonally complement to the null space. This is also very easy because, well, row space, well, if you just, so this theory, this is everything about the A. And if you take a transpose of A, and if you apply the same logic, then you are easily be convinced that row space must be also orthogonal complement to the null space. But those two guys they are subspace in Rn, and their dimensions are complementary, and they are orthogonal. So they are also. So you can I will not say too much in detail about this remark, but I guess you are easily convinced. All right. Let me try to find the basis of 4 fundamental subspaces of this matrix. What is the basis of the row space? Even though it looks like I have 2 different rows, but the second one is actually nothing but the 3 times of the first. So this is simply merely this guy is spanned by this vector, and by same reasoning, the column space is just spanned by this one single column, because the second column is just 2 times of the first. Okay. Now the question is, can you find out the left null space and the null space? Well, we know that this guy is orthogonal complement to this one. So, and since this matrix has rank 1, therefore this one must be one-dimensional subspace. So it suffices to find just one single vector which is orthogonal to this one. Then that must be the basis vector of this one, right? And well, can you think of any vector which is orthogonal to this guy? Well, I guess -2 and 1. Yes. Yeah, I just chose a random vector which is orthogonal to this guy, and I believe this is a basis vector of the null space of A, right? By using same trick, left null space is orthogonal to the column space. Therefore, I just randomly chosen a vector which is orthogonal to this guy, and I believe this guy has to be the basis vector of the left null space. Okay. All right. The last topic for today is the inverse matrix. hold on. So we know the inverse matrix. Inverse matrix was the notion of the inverse matrix exists only for the square matrix, right? So if you have matrix A, but if you have another matrix of another square matrix of the same size and multiply both of them together and if that equals to the identity, then we say the matrix has the inverse matrix. Okay. So this was our original definition of the inverse matrix. If I have n by n matrix, then if I can find another matrix B of the same size and which equals to identity, then we say B is the inverse of A. Okay. But today I want to introduce the notion of the one-sided inverse. So one notion of the one-sided inverse actually is true for non-square matrix. So I have an n by n matrix. So this is a rectangular matrix, not necessarily square matrix. And we say this A has a left inverse if I have another n by n matrix B such that B times A equals to the identity. So yeah, I have to be very careful about the, so n, so yeah, this n is right. So B, and this is left inverse of B. So B is the left inverse of A. Yeah, simply because B multiplied to the A to the left equals the identity. And the right inverse I mean by if I can find another matrix B such that if this time around, if I multiply matrix B to the right of A and then equals to the identity. And if I can find such a matrix B, then B is called as a right inverse of matrix A. Okay. So this is the left and right inverse. And this is the theorem, and it goes on like this. The statement that the theorem consists of two statements, and consider this system of linear equations, and if the system of linear equation has at least one solution for all possible choices of B in Rm, then in this case A has a right inverse, and in that case M is less than equals to N. M is less than equals to N. That means so in this case A must be a wide matrix. Okay, because row index is less than equals to column index. Okay. And number two, and in this time, if Ax equals to B has at most one solution, so that means you may or you may not have a solution, but if there is a solution, the solution must be only one. If this is true for all possible choices of B, then A has a left inverse B. And in that case, M is greater than equals to N. So in other words, A must be in this case, narrow matrix. All right? All right. Oh, sorry. I'm sort of running out of time. So since, I'm going to give you the proof of number one. And for the proof of number two, it will be left for the next lecture. Just let me go back to the assumption of the statement. Ax equals to B has a solution for all B's. So that means having a solution means that, B is a member of the column space of A. But I can find a solution for all such B's. That means the column space must be the entire Rn, right? So, all right. So in that case, so I can find solution for every possible choice of B. So if I just replace B by the standard unit vector, this one, then this equation, it must have a solution. Let me say x equals to xi. And if I multiply all these solutions, so if I multiply A by another matrix whose columns are exactly these solutions, then the result is going to be the identity matrix. Okay. Now, it remains to show that M must be less than equals to N. I'm going to prove by contradiction. Suppose that M is greater than N, then A must have at least N pivot, right? A must have at most N pivot. Number of pivots cannot exceed N, right? Because because of dimension reasons. That means column space of A must be at most N-dimensional space. That means this guy can never be able to achieve the entire space Rm, right? So which is contradiction. Okay. All right. So this is for today, and I will see you next time. Bye.